What we're going to do here is do the PowerPoint presentation for topic 1.1 in our Math 100 class, some basics of algebra. Here we'll be reviewing pretty much what I'm doing in class, plus working these examples. So with this and the additional examples that I've already done, ought to be the full program. For anyone that's absent, this would be a good review. So we're going to talk about algebraic expressions, equations, and inequalities, and sets of numbers. Start off with a little terminology. When we think of algebra, often we think of X, Y, and Z, and these are called variables that we can use in our calculations. So letters that can be any one of various numbers are called variables. Now, sometimes in an algebraic equation or expression, we'll sometimes see the number 5 or 4. Numbers like this are called constants. Now, when we think of an algebraic expression, it would be a series of letters and numbers plus signs such as minus signs, plus signs, multiplication signs, division signs. These are algebraic expressions. And here are some examples. So here we see a letter. This would be a variable. The 4 is a constant. There's a minus sign indicating subtract. Now this is part of the formula for perimeter, in which it's 2 lengths plus 2 widths equal the perimeter of something. And this is part of a formula to show slope-intercept. We'll be doing that in chapter 2. But these are all expressions. Now, if we have an equation sign in there somewhere, for instance, if we said that that expression equals that expression, then this is an equation. Now, another key term in this section is exponential notation. So as you read this, it says this is an expression right here where the a is considered the base and the n that's in a super case up here, this is considered the exponent. So something written like this is written in exponential notation. And what does it mean? Well, this is going to stand for some number of times that the base, in this case a, is used as a factor. So we say a to the nth or a to the n power is shorthand for what this shows here. Now in the case of this a where there is no exponent, there's actually a 1 there. There's always a 1 if there is no exponent showing. It's assumed to be there. Now here's a case where they're going to give us an example and they want us to use the area of a triangle. Now the area of a triangle is area equals 1/2 the length, or the base, times the height. That should be a b. And we just substitute the formula into it. 1/2 times 10, put a dot there, times, this dot up toward the middle indicates multiplication, 3.1. Now low, it indicates a decimal. Now notice what can happen here. We can cancel the 2, goes into there once, 2 goes into 10 5 times. So we've made it a little simpler, just 5 times 3.1 equals 15.5 feet squared. And then our next few slides, they actually show it. So it's 1/2 the base times the height, and you could do some canceling here, and there's our answer. And you want to identify the answer in most cases. Now this chart shows us the various types of rules that when we are working on a mathematical expression to simplify it, or in some cases equations to simplify, we follow a certain order. And we have the acronym, please excuse my dear Aunt Sally. And these are the letters that says you do parentheses and exponents first, going from left to right. Then you do multiplication, division, going from left to right, whichever comes first. If division is first, you do division first. And again, addition, subtraction last, but if subtraction is first, you do that. So from left to right, you follow these. And that's what they're showing in these rules for order of operation. Now I had that expression written on the board. And now let's try some examples. So here for the letter X, they want us to substitute a 2. So we then set it up. 2 times 2 plus 3, the quantity squared, minus 12 divided by 2, the quantity squared. And now, again, we could do some of this mentally, but you want to have enough work to support an answer. So this is going to be 5. 5 squared is 25. So 2 times 25 is 50. Minus, now we have to do this division, but before that we have to raise this power. So this is going to be a 4. 12 divided by 4 is 3. And we now can do our subtraction and get 47. Now they use a few more steps, but I'm saying as long as you provide enough to get an accurate answer, then that's okay. And we use this process called substituting. And there they show pretty much what we showed, a little bit more. And here they're giving you the rationale for doing it. All right, let's take a moment for this one. And again, we had the students write this out in class. So this will be 4 times, now x is going to be 3 squared, plus 2 times 3 times 2 minus, which is our 8 over there, 8. So 3 squared is 9. 9 times 4 is 36. This will be 2 times 6 times 2 is 12, minus 8. So we add these two and get 48, minus 8 gives us 40. So again, they're showing you protocol, procedure, strategy, and the work needed to support your answer. That's what we're looking for in your homework logs that we spoke of earlier. Okay, now another type of example you'll run into using the practice where they ask you to, is 8 substituting for x a solution for this equation? So you put 8 there, plus 12. Does that equal 21? Well, this is 20. That does not equal 21. So the answer here would be no. They're showing you another method where they sort of put a line, this side, does it equal that side? And again, the answer is no. Now, here's one of the major parts of this lesson, and that is sets of numbers. Now, when we talk about numbers and sets of numbers, it's like we're talking about sets of dishes or sets of knives or tablecloths or something. But in mathematics, we talk about sets of numbers, those numbers that are in a set. Well, we name a set, but before I do that, I want to create a number line. And these are what I did in class. So what's in the middle of a number line? Well, a 0. But when we think of the first set of natural numbers or counting numbers, our set includes a 1 as our first item. And if I put dots on the number line like this, I'm graphing the number set. Now I don't want to go all the way up to infinity here, so I'm going to put an arrow to indicate that this pattern continues. So this would be the graph on a number line of natural numbers, which are the counting numbers. Now, if we add a 0 to this natural number set, we get the next set, which are called whole numbers. This is now the graph of whole numbers. Now, there are numbers on the other side. For instance, a 1 has an opposite 1 on the other side that we say it's -1. When we add a -1 and a positive 1, it equals 0. So for each of the whole numbers, there are negative opposites there in a sense. And we can put an arrow to indicate it goes on. Now this is a new set of numbers. These are called the integers. It's the set of whole numbers and their opposites. And you would start at, in this case, -infinity. Use what I forgot to mention already, the 3 dots, which is an ellipsis, picking up the pattern, going through 0 and then into your positive whole numbers, and then again indicating the ellipsis that this is going to positive infinity. And to complete our graph up here, we would just put dots at these points. This is now the graph of integers. Now, while I'm using this line, are there other numbers on this line? And the answer is yes. For instance, between 0 and 1 is 1/2. And a little bit to this side is 1/3. Now, if I convert 1/3 to a decimal, it's 0.3 with a bar indicating it just keeps repeating 3. The 1/2 becomes 0.5, and there's nothing else after it. So here, this fraction repeats, this fraction terminates, that is, there's only one and then it stops. These kind of fractions, along with the integers, are called rational numbers. Now we're going to get that in the next slide. I'm showing it here because of my number line. Now if I go a little bit less than 1/2 right there, I get the square root of 2, which has an equivalent decimal of 1.414, and it just keeps going on and on and on, bouncing around, never repeating and never ending, terminating. For those kinds of numbers, the square root of 2 is what we call irrational. Now, all numbers that are under the radical sign are not irrational. For instance, the square root of 4, where they're telling you this is an operation, take the square root of 4, which is 2. 2 is a counting number, a whole number, an integer, a rational number, and all of the numbers on the number line make up a set called real numbers. Now, all numbers that are not perfect squares, such as 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, those are all perfect squares. If they were to be found under the radical sign, they would be rational numbers because they produce a fraction, in a sense 2.0, that terminates. And all those other numbers that are not perfect squares, starting with a few such as 2, 3, 5, 6, 7, 8, these are not perfect squares. So if they were found under the radical sign, all of these numbers would be irrational. And another famous irrational number is pi, which we approximate as 3.14. You'll be using that a little bit later. Okay, so there's a summary of all the sets of numbers that we'll be covering in this course. These are the real numbers. And I'm going to give up my picture here as I go to our next slide. Now, when we write numbers, this is another key word for vocabulary, we use what is called roster notation, where we put braces and then the items separated by commas. Now, what would this actually be the roster of? Well, for that, we use what is called set builder notation, where this is red, the set of all x is such that, that's the vertical line there, x is an even number between 1 and 9. Now, this might be modified a little bit to be acceptable, but this is an example of set builder notation. This is an example of roster notation, which is part of our lesson for topic 1.1. And you will need that for practice and later the quiz me's. So the rational numbers, we said, when we divide the fractions and the expression does terminate as a decimal or it repeats in a pattern, those are rational numbers. Now, if the decimal doesn't repeat and doesn't terminate, then it's considered an irrational number, and that's what we're looking at on this page. And the square root of 5, since it's not a perfect square, and pi are typical ones that are irrational. Now, all of the numbers on the number line are real numbers. And here's like a little summary of everything. Everything on the number line is a real number. Then some of them are rational. When you convert it to a decimal, it repeats or terminates. Here, it doesn't repeat or terminate. Those are the irrational. And then these are the various sets. And you'll be asked on your practice and later the quiz me to do some of these. So take a moment. We did this in class. What are these? Okay, going on now to wrap this up. Hopefully you have them correct. So going through them, this is an integer, rational and real. This is only rational and real. Whole number, integer, rational and real. This is a fraction. This is 5.5. So it's rational and real. This is the only irrational, but I don't know if you notice, all these numbers are real. And this is a natural number now. This is whole, integer, rational, and real. And 12 over 2 is equal to 6. So it's a natural number, a whole number, an integer, rational, and real. So you'll be doing your practice and later your quiz me's, and that will be your challenge. Are you getting these right? Do you know your sets of numbers? And here they are. And I've added this slide. It's interesting. See, we have a little typo over here. Practice examples. Now, since I spotted that, no bonus point for that one. And that completes it.